Yeah, good morning, students. Now, in the previous class, we had a discussion on memory delays. Now, today, the classroom discussion topic is on branch delays and branch predictions. So, the objectives of today's class are after this branch delays and branch prediction. So, you are able to this session will develop the students' knowledge on the issues related to branch delays and branch prediction outcome. So, actually, coming to this point, what do you mean by a branch delay? So, generally, we had previous discussion that there are two different types of branches are there. One is called it as unconditional branching, and another one is called it as a conditional branching. So, whenever we have a branch instruction, for example, if you take this instruction ij, if you take this, so it is a branch to ik instruction. So that is the unconditional jump we are performing, so that in between we have ij plus 1 and ij plus 2 instructions are there. So if we have this type of branchings are there, so what is the delays that we are able to introduce to execute this type of branching? So the clock cycle 1, during this clock cycle 1, so the ij instruction will be fetched, and during the clock cycle 2, the instruction is decoded, ij instruction is decoded, and during the same clock cycle 2, the instruction ij plus 1 is fetched. Then during this clock cycle 3, so the ij instruction is enter into the computation stage. During this clock cycle 3, the ij plus 1 instruction is in decoding. Then what will happen here is that during the same time, the clock cycle 3, so the ij plus 2 instruction is fetched. So now, because once we decoded that instruction and once the computation is done, we are able to identify that this instruction should be branch instruction, unconditional branching. So we are performing a delay we are doing here. So how many clock cycles has to be delayed to complete this branching? So this is what we are calling it as this during the clock cycle 4, clock cycle 5, clock cycle 5, 6 and 7. So if you see that during this clock cycle 7, during this clock cycle 6, if you see that here, what is happening? So there is no operation that is done here. We are just simply delaying that instruction execution. So ij plus 1, ij plus 2. So once the branching is done here, during this clock cycle 4, the ij instruction is fetched. Clock cycle 5, it is decoded. Clock cycle 6, it is computation is performed, and then clock cycle 7, memory operation is done, and clock cycle 8, the write operation is done. So that is, this is what we are calling it as the branch penalty we are calling it as. So from this clock cycle to this clock cycle, so that is the clock cycle 2 to clock cycle 3, we have a penalty, branch penalty is there here. So that means here reducing the branch penalty requires the branch target address to be computed earlier in the pipeline rather than wait until the compute stage. So it is possible to determine the target address and update the program counter in the decode stage itself. So that earlier instruction, if you take it as it has taken this 8 clock cycles, now we are able to complete that delay if you are able to compute the destination address, target branch target address. If you are able to compute early, then we can able to reduce this branch penalty, we can reduce. Okay, so that is what we are seeing in this decode cycle of this particular instruction. So thus the instruction IK can be fetched one cycle earlier, reducing the branch penalty to one cycle only. Previously we required two cycles here, so branch penalty is requiring two cycles here. So we are reducing the branch penalty if you are able to identify the branch target address early. Okay, that is what we are doing here is that. So then coming to the second type of branching statements, which we are calling it as a conditional branching statements. So let us consider a branch statement like this: branch if contents of R5 is equal to contents of R6. Then we are going to this loop. Okay, so this is what the example for a conditional branching. So for pipelining, the branch condition must be tested as early as possible to limit the branch penalty. Similarly, the comparator that tests the branch condition can also be moved to the decode stage. That is a comparator which is testing the branch condition. It has to be moved to the decoding stage so that enabling the conditional branch decision to be made at the same time that the target address is determined, so that we can reduce the branch penalty, we can reduce that. So in this case, the comparator uses the values from the outputs A and B of the register file directly. Moving the branch decision to the decode stage ensures a common branch penalty of only one cycle for all the branch instructions. So if you take an example here, we are making use of this add R7, R8, R9. Then branch if contents of R3 is 0 to a target. So this is the IK is the instruction which is labeled with a target. So assume that the branch target address and the branch decisions are determined in the decode stage. At the same time, the instruction ij plus 1 is fetched. So the branch instruction may cause instruction ij plus 1 to be discarded after the branch condition is evaluated. So if the condition is true, then there is a branch penalty of one cycle before the correct target instruction ik is fetched. So if the condition is false, then instruction ij plus 1 is executed and there is no penalty. So in both of these cases, the instruction immediately following the branch instruction is always fetched. So the location that follows a branch instruction is called it as a branch delay slot, we are calling it as. Okay, so the location which follows a branch instruction is called it as a branch delay slot, we are calling it as. Fine. So the add instruction is always fetched and executed even if the branch is taken in this particular example. So the instruction ij plus 1 is fetched only if the branch is not taken. Logically, execution proceeds as though the branch instructions were placed after the add instruction. So that is, branching takes place one instruction later than where the branch instruction appears in the instruction sequence. So this technique is called it as what we are calling it as a delayed branching technique. So we can make use of this delayed branching technique so that we can reduce the branching delays, we can reduce that. So now the reflection spot is that what is the branch delay slot? Then branch prediction. So we have the two different types of techniques for branch prediction. One is a static branch prediction and another one is a dynamic branch prediction. So we will see that static branch prediction here. Assume that the branch will not take in and to fetch the next instruction in a sequential address order. So if the prediction is correct, the fetched instruction is allowed to complete and there is no penalty. However, if it is determined that the branch is to be taken, the instruction that has been fetched is discarded and the correct branch target instruction is fetched. So misprediction incurs the full branch penalty. So the branch prediction, a dynamic branch prediction, if you take that, so a dynamic prediction algorithm can use the result of most recent execution of a branch instruction. So the processor assumes that the next time the instruction is executed, the branch decision is likely to be the same as the last time. So that is the reason here. Hence, the algorithm may be discarded. This may be described by the two-state machine as shown below here. So branch not taken and branch taken. So if it is LT less than or L and T, okay. This is another dynamic. The four states are like this: ST strongly likely to be taken, LT likely to be taken, and likely not to be taken, and strongly likely not to be taken, SNT. So these are the four different types of states are there here in the state diagram. So based on this, here the transition state diagram is represented as a dynamic prediction mechanism in this particular figure. Coming to this lecture level practice problem, for example, consider the following code which is given in a C language here. So if you consider this condition while a less than 10, so branch instruction condition either true or false. So now if a, so we are going to this calculate the accuracy using 2-bit dynamic branch prediction for all the states. This is the lecture level practice problem. So the outcome of this session is that lecture outcomes is like this. After completion of this session, you will be able to analyze the issues related to branch delays and predict the branch outcome. Fine. So thank you one and all.